Hello, AB Calculus. It is Mr. Canfield. Today we look at Chapter 27, Definite Integrals. I'm restarting this video because I talked for 2 minutes and didn't say a whole lot a couple minutes ago, and I was like, no, I'm not doing that. Of course, I'm doing it again now. So, the new thing, the thing that makes definite integrals different than regular integrals is there's this A and a B slapped on them. And we can jump pretty far and actually calculate a definite integral. I want to calculate a definite integral before we actually talk about anything else. I just want you to understand how you calculate a definite integral. We'll talk about what it means and so on and so forth. So check it out. Let's say we want to do the definite integral of 2x dx from 3 to 4. You might notice there's one new thing here, and that is that it goes from 3 to 4. So let's look at how this works. Let's talk about that. So remember, when we're taking an integral, we're saying, hey, what gives me the derivative 2x? Well, something that gives me the derivative 2x is x squared. And you might be used to, you better be used to at this point, saying plus c. Definite integrals get a little bit different. This is the last time you're going to see this when I write those, and let's talk about why. So the way that we notate this now is we say, draw a line. Sometimes people like box it off like that. 3, 4. And the way that this works is we're going to take this expression and I'm going to take x squared plus c, and subtract them. I'm going to plug in 4 to the first one and 3 to the second one. So let's see, we get 16 plus c minus 9 minus c. Hey, look, plus c minus c, those go away. 16 minus 9, we get, I almost said 5, 7, okay. So, completely without context, we can say the definite integral from 3 to 4 of 2x dx is 7. And we'll talk about what this means in just a minute, but I really want to make sure I emphasize something here. What happened to the plus c? Here's the thing. This will always happen. And so when we do definite integrals, we leave out the plus c. We don't need it. And if you're like, oh, but like, I'd rather have it, just get used to not doing it. Nobody does it. You will get looked at funny for doing it. So don't, like, get out of doing that, at least in public. So, yeah. All right, so that's a definite integral. Let's go through and look at these notes and what does a definite integral mean, blah, blah, blah. So we know that the derivative of some function is the slope of that function, essentially, right? It's the slope of the tangent line to the function, but it's the slope. Derivative is slope. Well, integral also has a visual connection. It has a geometric connection, and that connection is area. So not only are we able to use derivatives to find slope, but we can use antiderivatives to find area. And that might not immediately sound useful. Eventually we will discover how incredibly powerful integrals are. Integrals really were the reason that calculus came about the way that it did. That's really what Newton wanted to know, was the integral. So let's see. Yeah, so he talks about some theory things. We're definitely going to look at the theory of how an integral exists and stuff like that, but all you need to really understand is that the integral is area. And area specifically, it's the area between the x-axis and the curve. So, for example, if I took that's a and that's b, and this is f, right? If I took the integral of f of x from a to b dx, it's going to equal whatever this is. But if I looked at it from b to c, you know, we normally talk about area as being a positive thing. This would actually be a negative area. So above the x-axis is a positive area, below the x-axis is a negative area. And I'm going to use that phrase negative area, even though that's inappropriate. Perhaps a better way to talk about integrals is accumulation or accumulated area. So like here we are gaining area, here we are losing area. Snowfall is a really good way to talk about it, like snow falling and snow melting. Oh, we should also talk about that. Integrals always, we always put the lower bound here and the upper bound here. It's always low to high. Well, and it's always, like that one always goes second and like subtract this one. That's the more important thing. This one is always the one that's getting subtracted. That's always the first one. So for me, visually, it goes like that. Okay. So you can actually do, you can do integrals very similarly to the way you can do derivatives. Here's a whole bunch of properties, and each of these properties is more or less a common sense property, but let's look through each of them. So our first one, this one is so silly. The integral from a to a of f of x dx is equal to 0, okay? That's our first property. If the integral goes nowhere, then if there's no width, there's no area, right? So that's our first one. This second one, this is a beloved trick of the AP exam. They love this one. If you go from B to A, that is the same as pulling a negative out and going from A to B. And like, if you think about it, you know, we were just, where did I put the paper? You know, a minute ago, the paper, you know, it had the 1 minus the other. Well, if you want to do the other minus the 1, it's going to be the opposite, right? Because 3 minus 4, 4 minus 3, you get the same number, but it's an opposite. And that's all this is saying. Reverse the bounds, you get the opposite. Let's see. Here's another one. This is another very good one. From A to B, if there's a constant on f of x dx, this is the same as if you pull the constant out and then go from A to B, f of x dx. So, however, 3x, let's say we had 3x times x squared minus 4. Let's just say we were looking at this. I'm not going to do the whole problem, but some people look at the 3x and they go, oh, I can pull 3x out front. Oops, 4 to 5. And I hope that alarm bells are ringing in your brain. This is close, but this is not allowed. X is not a constant. Some people might try to pull the 4 out. You can't pull the 4 out. You can only pull a constant that's multiplied by the whole thing. So this 3 is multiplied by the whole thing. So I could pull the 3 out front and leave the x times x squared minus 4 inside. Like, that's totally fine. Number 4. Just reminded of my college professor. Every time the integral of a sum is the sum of the integrals, he would say this all the time, and it just went in one ear and out the other. It's simple, though. It's so simple. I'm not even going to rewrite it. If you have an integral and it's two things added together, you can just break it up, do two separate integrals. We've already done this, though, and the bounds stay. That's the main thing, A to B, A to B. This last one, this is like the transitive property. That's like saying if I go from my house to the mall, and then I go from the mall to school, I could just say I went from my house to school, right? You can leave out the middleman or the midpoint. So like if I go from A to B, f of x dx, and I add that to B to C, f of x dx. Notice how this is in the middle. Find the area from here to here. Cool. Find the area from here to here. Cool. We're really just finding the area from A to C. So, surprise! And now we can do a bunch of problems. Below, you are given the graph of f of x formed by lines and a semicircle. To me, this does not look like a semicircle. It looks like an oval, but we're told it's a semicircle. Great. So, using the properties we just talked about, we want to find all t of these areas. So, yeah, I think I am not going to do every single one of these, but I am going to jump around and, yeah, what I would say is see what you can figure out. But if you're completely lost, you know, stick with me for a little bit. So let's see. The integral from, wait. Right? If you start and end at the same place, it's 0. Do I have any more that are like that? Dang, I don't see any. Okay. So from 0 to 1, f of t dt. Well, wait, it's f of x and it's f of t. Huh? Remember, in integrals, the variable doesn't matter what it is so long as this variable and that variable match. So we could have used f of, and then you could have written your first initial for all these. And if your first initial is t, then win-win. So from 0 to 1, it's really just saying what's the area under the function from 0 to 1. And if you look, you know, it's a rectangle, base 1, height 2, area is 2. I like to mark up these diagrams. So like, now it's asking me for the area from 1 to 3. So that's this triangle, right? We know the area of a triangle is equal to 1/2 base times height. Looks like my base is 2, my height is 2. So that's 2 times 2 divided by 2, which is 2, right? Because it's half of 4. And then I'll talk about that one in a minute. So from 1 to 3, it's going to be 2. So what's our area from 0 to 3? Well, that's just these 0 to 1 and 1 to 3 added together. It's just all that added together. So it's 4. Then we're going from 3 to 6. Okay. So from 3 to 6, I personally like to break these up. In this case, it's actually foolish to break it up, but I would find that little triangle, find out that's -1/2, and then break that one up and find it. But if I look, it is one big triangle with base 1, 2, 3 and height -1. So 1/2 times base times height. This is -3/2. And I'm writing -3/2 because remember, even though I'm talking about this as area, above we count as positive, below we count as negative because it's more of an accumulated area, or like gaining and losing money, gaining and losing snowfall. So from 3 to 6, I got -3/2. Oh no, but now I want to go from 6 to 3. Oh, it's so hard. Oh, it's just the opposite. Quick sidebar, if you got E wrong, F would be correct if you wrote the opposite of what you got for E. Like if for some reason your brain fell out for a second and you wrote 83 for E, F would be -83. You would get full credit for that, for F. Because it shows that you understand that reversing the bounds just makes it the opposite. Whoa, now I'm going from 0 to 6. So the area from 0 to 6 is going to be 2 plus 2 minus 3/2. It's literally start here, end here, add up all that area. Add above, subtract the stuff below. So that's 4, that's 8/2. So 8 minus 3 is 5. So 5/2. 6 to 10. Ooh, they said this was a semicircle. So I know the area of a total circle is pi r squared. So a semicircle is pi r squared, then divided by 2. That's it. So my radius of my circle, there's my center, that's 2. So radius is 2, squared is 4. That's 4 pi over 2 pi. So the area of this total semicircle is 2 pi. So from 6 to 10 is 2 pi. Oh no, I'm going from 10 to 6 now. Oh, can't figure that out. Oh, too hard, okay. So from 0 to 10, you just add them all up. Oh, we should talk about that. So if 0 to 6 is 5 halves and 6 to 10 is 2 pi, you would just write 5 halves plus 2 pi. You don't need to get the decimal or anything. Leave it like that. Walk away. It's good. Throw a negative out front. You got that one. Ooh, -1 to 0. What kind of shape is that? All right, there's a couple of ways to do this. I am going to, because of what I know we're going to be doing soon, I'm going to address it in a very specific way. You could definitely find the rectangle and then add the other triangle on top. I would prefer to explain this through the concept of looking at it like this, okay? I know this side is 1, I know this side is 2, and I know this side is 1, 2, 3, 4. Do you know what kind of shape that is? That's a trapezoid. Remember, a trapezoid is 2 parallel sides connected, however. I think it's 2 parallel sides and then 2 non-parallel sides. I think that is a requirement. It's not a parallelogram. Ooh. Should have double checked that. But anyway, the area of a trapezoid is very similar to the area of a rectangle. The area of a rectangle is base times height, right? Well, the area of a trapezoid, the problem is there's not one base, there's 2 bases and they're different. So the area of a trapezoid is still similar. It's going to be base times height, but it's going to be the average of the 2 bases. So the way that we average 2 bases, you add them together, divide by 2, right? So we'd say 1/2 base 1 plus base 2. That's the area of a trapezoid. So this trapezoid is 4 plus 2 is 6. So 1/2 of 6, and our h is 1. So it's 3. The area of this is 3. And if you're like Canfield, I did that really easily by going 1, 2, and then that's another 1 because it's 1 and yeah, that's great. That's great. I wanted to introduce this idea. We're going to be using this later. This concept, we're going to be using it later. It's a sideways trapezoid. That's the height. There are 2 bases. So I got 3. And let's see. The next thing that I should talk about is this. R and S. Because this is just, you can check the answers on Schoology. It's just more exercise of going through and doing it. But this down here, it says, so whatever we get in Q, R is the absolute value of it. So if I got 37, R is 37. If in Q I got -37, R is still 37. It's whatever this was, it's the absolute value of it. It's either positive or it gets turned to positive. If for some reason the answer is 0, which it's not, then it would be 0 here. Let's talk about S though. S says, but what about the area between -10 and 4 of the absolute value of our function? So I'm just gonna draw a so here's the big difference. This one, what it does is, if this is f of t, sometimes f of x, sometimes f of x is negative. So what it does is it actually takes, any time that it's negative, it mirrors it and makes the positive version. And then now we add all these areas up. So this, that -3/2 is going to be that negative 3 halves is gonna be a positive 3 halves now. This negative a half is gonna be a positive a half, that sort of thing. Add all those up, that's the main difference. And then t, the only thing that I would do to dress up t is I would pull out the negative 2. And I could reverse the bounds, right? And go from negative 1 to 1, pull a negative out front, wait, double negative. So now I just take that error. Well, hey, from negative 1 to 1, that was 3 here, and that's 2, so that's 5 times 2 is 10. So, in the next video, we'll continue on in this chapter. I just want to keep these chopped up. If you want, I would say go do some practice. If this wasn't practice for you, if this was learning for you, go to the problem like this in the homework. Do some of those practice, try them out, and then we'll continue on in the next video. See you there.